explain what these things here were, and I started drawing some photos up there. If we roll down to here, we get a better idea of what these shapes are. This is an angle, this is an I-beam, this is a parallel flange channel, and the other two members you don't usually use, but you'll see them detailed here, and they're called a hollow circular and a rectangular hollow section. There's also what we call a T-section as well. Now in the assignment you've got a unequal angle, a UA, and you've also got a universal column and a universal beam. Now, a chance for someone else to get a half a mark, not the two that answered the questions in class. As you can see here, I've got the way how we call these things up. When I say call up, that means the note you put or the label you put with an arrow to these particular members. And it says here the old way is, for example, 760 by 270 by 244 kilogram UB, universal beam. But the new way is, as in from about the year 2000 onwards, is called as a 760 UB 244. Why have I put the old way there? Any answers on that?
Dimension.
Because
It shows dimension.
it does show the dimension in the other direction, yes. But why would we be concerned about what the old way of calling up on a drawing is when we're past the year 2000 now and we call it up as the new way? Yeah, but, well, yes, some people may be stuck in the year 2000s, like I am with my clothes. Okay, so you are about to embark on a structural career in a design office drawing up structural buildings. Most of your work is not going to be new buildings, it's going to be add-ons to existing buildings.
Yeah, I see.
So the first thing you'll have to do is go and get the old plans out
Yeah.
and go, well, what actually is in there? Because unfortunately with steel, often it is covered up by, timber and other things. But if you've got it on a plan that it's a 760 by 270, 244 UB, you now know the size, and if you're connecting onto it, you can do the structural calculations to see if it can carry the weight you're looking at, and you can put the new member on there, and you can call that up. You can draw it up, and you can call it up accordingly. So, yeah, this building is pretty modern. It won't have any of the old call-ups, but the one over in 114, 112, 113, that's an old building. And I know for a fact, I've seen the old plans to that. That's a civil defence building, you know. So, yeah, if you ever had to get a job adding on to that one, you would be looking up all the steel members. Well, I wouldn't want to add on to that building anyway, but yeah. The other thing is sometimes they do actually gut a building completely, take everything out, start from scratch, but leave the concrete or the steel there, and then continue on. And you can't get an idea of the price unless you know what's actually in the building. Connections. Bolting is the most common. I've already said that. It is a question in the test. They did a lot of rivets in the old days. Riveting was the sort of common way to put steel together. Most of the older bridges are riveted, but they did find out in all sorts of ways that the rivets were the weak point on the bridge. Obviously, if they all pop, suddenly the structure falls apart. So they very quickly realised that the rivets had to be, in bridges particularly, they had to be protected. So the only way of protecting them was to paint them, and paint them every year. So the likes of the Auckland Harbour Bridge, there is actually people that have a job with a paintbrush, starting at one end and painting it all the way to the other side, and then they get there just before Christmas and they have a break and go back and paint it all over again. Sounds like a really good job, doesn't it?
That's what they're doing on the Harbour Bridge, right?
That's what they do, yeah,
Yeah.
because it's absolutely full of rivets.
Yeah, it's gonna take like six to 15 years, they say, in
To-
the news.
to
The
do-
painting job,
Is this a different type of painting job, or?
the painting the whole bridge.
Oh, no, they
Uh-huh.
do it and then they start again at the other end.
Yeah.
It takes about a year to do it, but they have to do it every year.
Yeah.
Yeah.
This time
Yeah.
they say they're gonna do the completely whole bridge painting through 6 years.
Oh, okay. I've had the privilege of going over the one over in San Francisco, the Golden Gates Bridge, right? And they run into money as they constructed it. They couldn't afford the paint, but they could afford the, what they put on rust-proof, the seal coat. It's a horrible orangey brown colour, right? And the story goes that the town mayor went to the people and he convinced them that that colour was beautiful and that they should paint the bridge because it matched in with the background, which was a kind of a browny, orangey colour. And the people agreed, and so therefore his bridge doesn't need as much painting because they're painting it each time with this rust-proof brown.
Stakeholder management, eh?
Beg your pardon?
Stakeholder management.
Yes, yes. So that's an amazing story, and he was one of those really pushy guys that got things done, and they said they'd never build it. He built it. I don't know his name, but I did a tour of there where you go over on a bus and that, and the guy gave us all the facts. There is a question on the best type of connection. Generally speaking, we don't weld as a way of connecting metal these days, mostly because of the fact that everything on site, you know, health and safety, bringing all the gear on site. Sometimes they have to clear the site while the welders are working. Well, they didn't do that on the Fletcher's site. And
In the CC.
yes, the ones that created the fire, and yeah, somebody left one of the machines on, and it just, well, they went and had a cup of coffee, which was more important than protecting the building, and it went up in flames. I was actually in the city that day, and I saw the flames and thought, that's a bit odd. Oh, they must be under control. I don't know if you remember, but they had to let it burn for quite a few days.
We see it every morning coming in on the motorway.
Yeah.
A lot of the city's gone there for a while.
Well, that was caused by a welder, once again, doing his work training on site and not at a place like Unitec. Okay, those things there are in the test because it's kind of like what you think about when you're choosing what sort of jointing to use. On the subject of bolts, not that bolt, it's a bolt called Usain Bolt. He was the man a few years ago. He's kind of not anymore. I don't know if any of you remember him. Every time he finished, he did the lightning bolt strike.
Yeah.
There's some pictures of some different types of bolts there. The choice tends to be relative to the job. So if you've got a smooth head on the bolt, usually that's because you don't want anything to get caught on the nut. So it might be on a handrail on a bridge where people's hands are going to go along, or it could be on the bridge itself where people are walking. You don't want them to trip or slice their feet. There are industrial bolts, and there's also engineering bolts which are a lot stronger. They're usually called black bolts. And then there's just your commercial ones that you would buy off the shelf cheaply at Mitre 10 or whatever, and they might be just for a cheap inside type job rather than a proper construction job. With steel, generally we don't use washers. We can, we generally don't. With timber, we tend to use washers so that the nut doesn't keep going into the wood. Alright? And sometimes you get joints where you have steel and timber, and it depends what the washer's up against to whether you use a washer or not. And there are different types of washers. There's ones which won't release, like as you're tightening them up, they won't untie them. And there are there are washers that come as a square washer versus a round one as well. And also with bolts, there are bolts that go into concrete. You've got one on your assignment called a Dynabolt. So that will go into the concrete hole, and then as you tighten it up, it spreads out like that. If you look that up on Google, you'll see as you're tightening it up the top, it starts spreading out like that, so it won't come back out of the concrete hole. Yeah. So there are other ways to join the concrete. You can use various glues or substances, and also you can set the bolts into the concrete so that they're on a steel plate, and the plate's set in there, but the bolts are poking up out of the concrete. The issue with that is you've got to get your drilling perfect on the steel, and that's quite an art to get that so the steel slips over the bolts.
Are they slotted though?
Yeah, you
With
can have a,
radius slots in it, so you can.
yeah, so there is a
Real through a rotation.
correct, you can have slotted holes and do it that way.
Much quicker that way.
Yes, yes. So that's in my notes as well somewhere there. If you have a slotted joint hole, the slotted hole looks a little bit like this,
Radial, yeah.
and there's your nut or your bolt, sorry. Well, that bolt can sort of go anywhere along here, and you can move it and it'll still fit over the steel plate will still fit over the hole, right? But then you tighten it up. That's the only trouble, is that it's very hard to tighten up when it's a slotted hole, because there's more slop in it. So sideways movement, you're a little bit vulnerable for that. But generally speaking, they do use that when you're going into concrete. Then we get into what's basically bolt design or bolt and plate design. The things that you need to remember, and I have put this in my test, so there's a page to mark for the test. Remember, you'll be having an open book test, so you can flick to this page. The pitch is the distance between the bolts lengthwise. We also have an end distance, as you can see there, and a edge distance, end and edge. And my test is a question on end and edge, and that sums it up there, but in the test it's put in such a way that you need to look at that diagram to figure out which is which. Obviously the end of the beam is the distance to the end of the beam, it's called the end distance, and the edge is on the side. Now, with all bolting, we have a minimum and a maximum. And the reasons for that, I'll just flick to the next little sketch. The reasons for that is that if we have, if there's too big a distance between bolts, we get this thing here called buckling. So you imagine a plate on the ground being bolted into something, but your bolts are too far apart. So when there's pressure and put onto the plate, it can buckle. Whereas if you had more bolts in there, it would stay down. And then we also have bursts, and that title here should be for below. And we have things called bursts between holes if they're too close together. So a crack will start and then it'll burst between the two holes. And we have end splits, which is when it's too close to the edge and a crack will start forming and then it will split to the edge. Now, it doesn't seem like much on those sketches, but as you can know from that thing that fell over, the power pole thing, power line up north, that pole, only a few nuts missing, and that was a weak point, and off she went, the whole thing. So your job as engineering designers, there is one other thing called a back mark. There we are, a back mark. And that's mostly used on angles to the edge point. You have to dimension to the holes, so remember that when you're doing your detail, for me, or two details. But B, you have to do the maths behind it as well. So the maths, let's take a simple plate. You get a plate design like that. The maths for the shortest distance, so the minimum equals 2.5 times the diameter of the bolt. And if that is called up as an 18 millimeter diameter bolt hole, so that's the hole, 18 diameter. What size is the bolt? 16, correct. So 16 bolt, 16 or M16 bolt, all right? So 2.5 times 16 equals 40. So your minimum equals 40. So the minimum applies to there, and there, and there, and there, all around. So the next thing to calculate is what is that distance there. And that has a maximum up there on the board of 32 times T. 32 times T, where T equals the thickness of the plate. 32 times T. So if the plate was 10 millimeters, it would be 320. So 10 millimeter plate equals 320 as your maximum before you have to put another bolt in. However, there is, if you look up there, it says the compression or tension shall not exceed 32 T or 300. So we actually have to drop that back to 300. I'll just go over that again for those that are over here and can't, they're just looking at my back. We have a plate, 4 bolts. The hole in the plate is 18 millimeters diameter, which means you take 1 millimeter all the way around, so that's minus 2 millimeters, equals a 16 millimeter bolt. We call that an M16, okay? Machine 16 bolt. So the calculation, 2.5 times the diameter of the bolt, 2.5 times 16 equals 40. So the minimum around the smaller parts is 40. Work out the maximum is 32 times T, but there is also a proviso there of 300 as your maximum. Now if that had been an 8mm plate, it would have been 256, because I'm really very fast at math. And I also have the answer over there. So 256 is less than 300, so 256 would be the maximum. Yeah. You still got a smile on your face because of that half mark, haven't you? You can see that. It's made your day. It's made your day. Go downstairs and start handing money out to everybody. Okay, that's how we do plate design. Now if this plate here had been, let me see, 300 plus 40 plus 40, 380, then that would be fine. You would have the gap here would be 300, that would be 40, that would be 40, that's 380, no problem, easy plate design. But if that was 400, you would have to put another hole in, or you move these bolts down by 10 mil. So you'd end up with 40 on there, 50 on there, 50 on here, and 300. 50's fine. It's just that you start by trying to get it to the minimum first. Remember grandmother's quilt when you're doing the reinforcing? Remember grandmother's quilt when you're doing this. Push it right to the edges. Okay, I have pretty much covered this except for one thing, and Lance has gone out, so whoever tells them this, you can charge them for this. We have a weld on our assignment, and every year I do this because those that don't turn up to class don't find it out, but you can of course charge them. Our weld on our assignment is going to be a 6mm fillet weld. The only problem with that is you're going to have to figure out yourself, like the compaction factor, what the symbol is. Luckily, I've got some notes here to help you. There's some notes there on bolting that you can use in your assignment, and there's some notes there on dimensioning to bolts, and what bolt holes look like, the dark ones compared with the open ones when there is a bolt in there with a centre line. There's some very good descriptions of things there which I've got in the test, particularly the splice, the lintel, the portal frame, the stiffener, and the purlin up there are ones I can remember that are questioned in the test. So a good page to have open or when you start your test, because if I've got 5 questions on there, you've got a good chance of one of them popping up or two. So this is what we call a weld symbol. I'll just go over that as best I can. That points to the actual weld. So when you're doing your assignment, you're drawing up your elevation, you've got an arrow pointing to it. It comes up a bit like a leader line, and this here, this little golf thing, is, it means a sight weld. We're not having a sight weld. Our weld is a shop weld. So no arrow, no flag on me. We are doing an all-round weld though. It's going to be all round the and it's going to look a bit like this in plan view. So our plate is here, and our column is here, and when we show it in plan view, it looks like, how can I put this nicely, a schoolboy's beard. Notice I said beard, that's because I come from a weird part of New Zealand called the bottom of the South Island, and they speak like that, beard, like they do in one part of China as well. We won't say what. So here's your beard, and that's how you represent a weld in plan view. Now you have to do that detail as part of your assignment. So I'm pretty much giving you quite a lot of information away at the moment. Yes?
What was the arrow again? The arrow connecting?
Right, so the weld symbol is when you look at your elevation, and here's your plate, and here's your side of your concrete, right? And you will have the arrow going to it. I'll just take that out at the moment. And it'll come along like that. It'll have a circle on it, meaning an all-round weld. It'll have these beaks at the back like that. It'll have 6 on it. Now this is the bit, now this time you've got a choice of 1 and 3. Here's your choices. 1, like a shark's fin. 2, an upside down shark's fin. Or 3, 2 shark's fins. And that's your symbol on site. It's either 2, 1 at the top, or 1 at the bottom. Okay? And that will represent a 6mm fillet weld. Now if I was to zoom in on that, it would look something like this. There's your column coming down, which is this thing. The plate is welded to the bottom, and the weld on the plate would be a 6mm weld, would be this bit in here. If I zoomed even more in on it, that dimension there would be 6mm. And you'll see there's your weld there. You'll see that detailed a bit further on in my notes. So it's the width of the weld. Now, anyone tried welding before? I have. We used to have to do it as part of my engineering course. It's bloody hard. It's really hard to get to do it, you know, and also to get it 6mm thick. It's yeah, I know. And I struggle with icing on a cake, let alone, you know. Don't ask me why I was doing baking, but I tried doing icing once and I couldn't even write my own name on the top. So getting a weld 6mm exactly is a science, really. Good welders will be able to do that. And also, when I did it, I just did big lumps all over the place. But I think the 6 is sort of a minimum, you know, when you're giving it, you know. So that's what you're putting in your assignment, and you only found that out through coming to Unitec today. So as I said, anyone not in class, you can tell them and charge them for it if you want to. Charge lunch double. As long as I get half of that, I'll be fine. There we are. There's a picture of welding 2 rods together. So what they do is they do a V cut, and then they put the weld into the V cut. Here's 2 rods coming at 90 degrees. And here's what I was talking about, how they weld a member coming down at 90 degrees to another steel member. There's a one-sided weld. And now this little diagram here talks about fillet welding. And there's your 3 sharks. So you've got to work out from that which one it is. good thing is I've also got some more drawings of these things in a sort of a isometric view. There's an intermediate weld at different points. There's what the symbol looks like. There's a fillet weld with an upside down one. There's a fillet weld with two. There's another diagram. And here's your fillet welds here, with a one-sided one, a left-hand sided one, and hello, there's a double-sided one there as well. I think you're getting the clues, yes. Okay, here's my little hairy-faced boy, hairy-faced little schoolboy. Also, older gentlemen start losing the amount of hair they have on their beard as well. So that's what we call a shop weld all round, which is exactly what you're going to be doing.
It is what is it?
It is, your weld's a shop weld from, shop means factory or done in the factory, yeah. There's all sorts there. I could have put like 5 or 6 of these in your assignment. Welding isn't my strongest point from the day that they made me do it right through to my life experiences with structural. I've mostly been bolting. So I thought, well, I'll put something in there as a token gesture. We'll make it a 6mm fillet weld because I know what that is. But you may have these notes in a later life and someone turns up and says, for example, they might say, oh, we're going to do a butt weld, okay, and a square butt weld. Now, if someone said that to me on the street, I'd slap them in the face, but you can go to your notes and say, yeah, okay, I know what a square butt weld is. It's not exactly what Roger said it was. So I'm just adding to your notes. You probably won't get this sort of detail in any other subject. So it's nice to know these things, especially a site engineer kind of ends up having to know a bit about everything, even things I didn't really want to know about. You've got to be quite knowledgeable in all areas. If you're in a design office, there's always someone you can ask, there's always ways you can go about things, and you tend to be a little bit more focused just in one area. But when you're on site, all those 17 things you're going to be talking about in your presentation, a site engineer needs to know a little bit about all of those things in order for the site to progress. So that's my notes. I'm going to give you, what are we up to now? According to mine, it's 10:56. I'll give you a 4 or 5 minute spell, and then I'm going to go over how about we make it a 5-minute spell. You get touch base with your team, and then we'll get together and go over this class example in the last hour, not this one, the one that I'm going to make available. This one here, which is available on Moodle. Whether or not I've got it is another thing altogether. This one here. Alright, so after the break, I'll do this. Now, as I said, it'll be in the test, so 2 or 3 marks in the test. It will also be, you've got a universal beam in your assignment, you've got a plate in your assignment, and you've got an angle in your assignment. So when I show you how to do this, should make it really easy to do your assignment. This is not an area where degree students struggle. This is quite a good way to make up some marks. Alright, so make it 5.